Okay, folks, in this section, we're going to talk about something called green chemistry. And no, it does not mean that you're working with green things in the laboratory. And no, it does not mean that you're working with fruit and vegetable in the laboratory. As strange as that sounds, sometimes people associate the word green to those kind of topics, and that's not what we're talking about here. So we need to talk about what green chemistry is and how to perform green chemistry in the laboratory whenever we can. But before we do that, I always like to start you off with an incident, right? Something that you can take away and learn from other people's mistakes. And here's the incident that we're going to be talking about. So I'm just going to kind of simply read it to you like I did before. And it says, approximately 25 grams of calcium oxide, CaO, also known as lime, was used in a synthesis on an occasional basis. To save money, CaO was purchased in bottles containing 500 grams. A researcher failed to tighten the lid adequately after removing 25 grams of water vapor entered the bottle. The water reacted with CaO and the bottle broke, scattering the unreacted powder across the lab area. So the scenario is, what can you learn from this, right? Okay, well, first off, the key word here is a researcher failed to tighten the lid, all right? There are plenty of things that we can use in a laboratory that reacts with water. And water not only comes from the faucet, but water also comes from the atmosphere that we're in, right? So the air that we breathe has water. The room that we're in has some water content. And some of these chemicals and some of these compounds will react with the water to form a reaction. In this case, what happened is that the CaO reacted with the water and it basically solidified it a little bit more. So it made it almost like a rock. And that's kind of what you're seeing over here to the right-hand side. When that began to happen, these rocks became much harder, much more rigid, and it bursted the container that they were in, right? And this is actually something that's happened to us before in a laboratory. Sometimes students will go and they'll take containers off of the lab stock shelf, they'll use it, and they won't tighten the lid as tight as it needs to be. And water vapor will escape and enter into those bottles and will come in the next day or in a couple of days, and the bottle will be bursted on our shelf and we'll have to go back and clean it up. So this is something that you need to think about as far as the laboratory chemicals and the stock goes. Is there a reason that there's a particular label on the front of the bottle and maybe you're not paying attention to that label, and it will say closed tightly, or keep in the refrigerator, or keep in a dark room away from light? You need to make sure that you're reading those labels and treating the chemical bottles like they should be treated. It's the same as if you went to the grocery store, right? If you buy a bottle of pineapple juice off the store shelf, then you can keep it on the store shelf out of the refrigerator as long as you don't open it. But as soon as you open that bottle, you're going to read on the label, and that label is going to say refrigerate and maybe use within 7 days after opening, right? So you want to make sure that you're following the labels, not only on the food products at your house, but also our own kitchen and our own food product supply, which is our laboratory and our chemicals, right? Something else, it was used in a synthesis on an occasional basis. So the occasional basically means that maybe you didn't have experience working with CaO or realized what it could do. And because of that, you just took it for granted and you went into the laboratory and just measured something out, and you didn't put the bottle back on it as tight as it needs to be, and you put it back on the shelf thinking that everything was okay, and it wasn't, of course. So occasional basis is a key word here, because this shows that this person should have actually pulled up the safety data sheet on CaO and made sure that they understood the precautions and the hazards that were associated with CaO before they used it. So just a couple of little tidbits of information. Just kind of keep these scenarios in your mind, because these are actually things that have happened, whether it's in our lab or labs across the country, that they have reported that we can learn from, right? So we're learning again from someone else's mistake. Okay, so now we need to talk about green chemistry. And I want to talk about green chemistry because this is kind of a hot topic word that we're all kind of following nowadays, right? So way back when laboratories first came into existence, we could care less about green chemistry. And that's because we just didn't fully understand the concept of what green chemistry was or what our chemicals could actually do to other things. And then along comes green chemistry that made us feel a little bit better about ourselves working in a laboratory and working with these chemicals maybe on a daily basis. So green chemistry is basically a definition that I need to provide you, and that definition is the design of a laboratory experiment. All right, so let's say that we're in the lab and we're doing something and we're working with these reagents, and these reagents are getting mixed together that uses environmentally friendly chemicals. All right, so the key word here is environmentally friendly. All right, that's really what we're after. There's reagents that we will use in a laboratory, chemicals that we will use that we cannot dump down the drain. Okay, we do not want to dump those down into the drain because those will get recycled and probably pumped right back into a water system if we're not careful. Or the discharge of those chemicals could go into aquatic life on the outside of the building, and we don't want that to happen either. Whether it's working for an academic lab or working for an industrial type of setting, these discharges are very common, and I want to make sure that the discharges are not harmful. So me, being as ethical as I can be, would want to get away from these hazardous reagents and chemicals that can cause cancer and that can cause things to mutate and that can kill people or fish, right? We don't want anything to happen to the animal life either. So because of that, we're going to substitute these nasty bad reagents to something that's more environmentally friendly. And that's what we call green chemistry. And that's kind of where the word greens comes from, because we're thinking of the environment here. So one of the things that I want to also keep in mind is that these reagents can often be cheaper as well. So if I pick a more environmentally friendly chemical, then that's probably going to be a little bit cheaper. Not only is the reagent cheaper, but if it's environmental friendly and I can dump it down the drain or get rid of it through a discharge, then I don't need to pay a lot of money for basically someone to come and dispose of that chemical that I'm using in a laboratory. So I save money on disposal fees as well. So the reagents are less expensive and the solvents do not have to be specially prepped or sent off to a disposal or a landfill for them to incinerate them or whatever they do once they get them. So ideally, it's going to make a little better sense to me to choose these environmental friendly reagents when I can. All right, so it can save a lot of green, not only the environment green, but also the green as far as a dollar bill is concerned as well. So that's something that you want to kind of keep in mind. So here's a slide that basically tells you all the good things about green chemistry whenever it can happen. If you look at number 1, it says it will prevent waste. What that basically means is that I'm using reagents in the laboratory and maybe I can recycle those, right? So as long as I use it and as long as I use it properly, there's lab techniques that we can implement in a lab that can recycle and reclaim those solvents all over again. And by definition, that is green chemistry. Now, those could be still hazardous reagents. And if they're still hazardous reagents, that's okay because I'm not dumping them into the environment. I'm recycling and reclaiming them and reusing them over and over in the laboratory, and that by definition is green. Number 2, I maximize the atom economy. Basically, an atom economy is the concept of two reagents reacting together in the best way possible. It maximizes my product yield. So sometimes we'll mix two things together and we'll get 30% of what we expect to get. And then sometimes we can react two things together and we'll get 80% of what we expect to get. That's a much greater product yield and what we would call an atom economy, right? Number 3, less hazardous chemical synthesis. As a lab employee, that's very good for me, because if I'm working with reagents that are hazardous, then I don't really want to expose myself to them for long periods of time. I don't want them to get them on my skin. I don't want to breathe them in. Anything could happen as far as a lab employee is concerned. So if I take these reagents away and out of the picture, and I substitute those for more environmentally friendly reagents, then all of a sudden there's less hazard that's associated with me as a laboratory worker. And that really goes into number 4 as well, safer chemicals and products, as well as number 5, safer solvents and reaction conditions. All of that holds hand in hand. It's just telling you, good for you as a worker, good for the solvents because they're not as hazardous, safer products in the very end as far as cleanup goes. It's safer all the way around. Number 6, increase energy efficiency. Sometimes in a laboratory, I'll mix some reagents together, and I might have to put a little bit of heat underneath them, right? I've got to heat them up, I've got to get them to boiling, and then they'll start reacting. Well, that requires a lot of heat, that requires a lot of energy, and as far as the environment is concerned, energy is one of those things that we look at. So if I can choose reagents that I can substitute out that maybe doesn't require that heat, then all of a sudden I can increase the energy efficiency of the reaction. I don't have to put heat anymore under the reagents to get them to react. I just mix them together in a container or a flask and they start reacting and producing my product. Number 7, the use of renewable feedstocks, and we'll talk about that a little bit later. Number 8, avoid chemical derivatives, or what we would call protecting groups. A chemical derivative is basically like a side product, right? These are kind of unexpected products that could happen in my flask or my reaction, or it could be an expected product that I just do not want and I want to get rid of. So if we can minimize all of those side reactions that can happen and really drive the reaction toward the product of what I want, then I get a higher product yield, and it makes this synthesis route and this reaction a little more worth it. Number 9, use catalyst. A catalyst is something that will speed reactions up, and that's pretty important as well, right? I don't want to sit there and wait for a week for the reaction to happen. So a catalyst will actually play with the chemistry a little bit and speed the reactions up to make them happen much quicker. So maybe instead of days for the reaction to take place, a catalyst will allow the reaction to happen within a matter of seconds. And if I can find those and use them, then that's good because that's green chemistry. We're saving energy yet again, right? Number 10, design chemicals and products to degrade after the use. So once I make the product, and let's say the product doesn't get used as soon as it needs to be, we pump that out into the ocean, we pump that out into a river or a lake or a stream, or we dump that out into a landfill, I would want that chemical to decompose on itself, right? I don't want the chemical to stay around forever. I want the chemical to break down after a certain point in time and basically expire on me and change into something completely different. So if we can make products and use reagents that do degrade after a certain point in time, then that is by definition green chemistry because I'm looking out for the environment here. Number 11, analyze in real time to prevent pollution. So as I generate these products, I want to kind of look at those as that generation is happening to make sure that nothing is kind of getting out of line and that we're producing what we're supposed to be producing and nothing weird is happening that we're discharging into the environment. And number 12, minimize the potential for accidents. And really, number 3, number 4, and number 5 all relate to number 12 as well. If I get safer chemicals, safer reagents, if I make safer products, then all of a sudden I can minimize the potential for accidents in the laboratory. So if something does spill, whether it's in the lab or a chemical spill, once it leaves my company and gets on a tanker and drives down the interstate, if that tanker turns over and that solution or that chemical spreads across the road and goes into a nearby lake, river, stream, soil, or goes into the air, then this will minimize the potential for accidents that might happen with the chemical exposure. So those are the things that we're looking for green chemistry. And it's quite a bit, but at the same time, it's very important for us to follow these kind of rules when we're in the laboratory and we're making the decisions as a someone in a STEM discipline or science discipline would. So I'm going to stop the video here. I've rambled on for 15 minutes about green chemistry, and we'll come back and we'll pick up from this slide and we'll go through and take some more notes and learn more about green chemistry. So go take a potty break and then come back and I'll be ready for you.